Today we are going to discuss ionic equilibrium. So equilibrium what? Or equilibrium we have already studied in 11th, right? So what do you mean by equilibrium? So when the rate of the forward reactions and the backward reactions is same, right? So but here we are going to discuss the ionic equilibrium. So ionic means the new word is coming here, ions, right? So how the ions will be present in the solution and how the equilibrium will be established, that we need to discuss in this chapter, right? First, all of you know that what is the ionization process. So the process in which molecules of acid and bases and salts, when melted or dissolved in the water, dissociate into ions, are called ionization. So it's not like that all the molecules or will dissociate in the melted conditions or in the solution. Some of the molecules like acids, bases and salts, they dissociate in the solution, and this dissociation process is called ionization. Compounds which will give ions in the molten state or in the solution, usually aqueous solution, are called electrolytes. So we know that the metals are the good conductor of the electricity, right? But electrolytes are also good conductor when they present in the molten state or in the solution, because in the molten state or in the solution they undergoes the ionization process, produces ions in the solutions, right? These ions actually carry the charge or electricity. So but these electrolytes, salts or acids, they are very poor conductor of electricity in their original form. So if you don't dissolve these salts, acids or bases, so they are poor conductor. When we are dissolving these salts, acids or bases in the solution, or when they ionize, so they conduct electricity. So here you can see in the solid state they are the bad conductors. So solid sodium chloride or any other salts, acids, any other acids, so they are the bad conductors or poor conductor of the electricity. But when we dissolve it in the solution, so they ionizes and produces ions. These ions actually help to conduct the electricity. So now we need to understand that how many types of electrolytes are there. So there are basically two types. One is the strong electrolyte, another one is the weak electrolyte. So strong, what do you mean by the strong electrolyte? What do you mean by weak electrolyte? And what is the basic differences between the strong electrolyte and weak electrolyte? That we need to understand, right? So sometimes what happens, students get confused to identify which one is the strong electrolyte and which one is the weak electrolyte. So very simple word I am telling you. So all the strong acids, strong bases and salts, they are considered as a strong electrolyte, and weak acids, weak bases are considered as a weak electrolyte. So now these are the examples, right? So now what basis we are basically telling is the strong acids, strong base and salts are the strong electrolyte, or weak acids or weak bases are the weak electrolyte. That depends on the degree of dissociation. That is the new word or new term we are learning here, the degree of dissociation, right? So degree of dissociation means how much the compound get dissociated when we dissolve in the solution. So suppose if we dissolve any acid or base, it may dissociate 100%, it may dissociate 50%, it may dissociate 20%, it may not dissociate, right? So depending on the degree of dissociation, basically we categorize the electrolyte as a strong electrolyte and weak electrolyte. So usually we consider strong electrolyte 100% dissociate in the solution. Suppose if we dissolve sodium chloride, is a very good example of salt. So it will dissociate 100%. Means all the sodium chloride will convert to the sodium ions and cations and chlorine anion. So same thing happens for strong acid and strong base. So if you take HCl, if you dissolve or if you dilute it in the presence of water, so it dissociates 100% dissociation occurs. Means all the HCl molecules dissociated and gives us H plus and Cl. But this 100% dissociation do not occur in case of weak acid and weak bases. So that's why they are considered as a weak electrolyte. So the number of ions produced in the solution will be less in case of weak electrolytes. Suppose if we take 1 molar of HCl, so 1 molar of HCl will give 1 molar of H plus and 1 molar of Cl minus. But if we take 1 molar of weak acid, let's say acetic acid, it will not give you 1 molar of H plus and 1 molar of acetate minus, right? Acetate anion. So that's why weak acids are considered as a weak electrolyte. So they do not dissociate 100% in the solution. As a result, they produce less number of ions in the solution. So now what is the degree of dissociation? The degree of dissociation of an electrolyte is decides the fraction of the total number of moles of electrolyte that dissociate in its ions when the equilibrium is attained. It is denoted by the symbol alpha and given that alpha is the number of moles dissociated and the total number of moles. Suppose if we take a weak acid, let's say acetic acid, and if we dissolve in the water, right? So now if its degree of dissociation is 50%, right? Suppose let's say the degree of dissociation of this weak acetic acid is 50%. So if we take 1 mole of acetic acid, so in the solution 50% of acetic acid will undergo dissociation and 50% of acetic acid will remain as it is. So now 50% of acetic acid, 1 mole, it will produce 0.5 mole undergoing dissociation. So that means it will produce 0.5 moles of H plus and 0.5 moles of acetate anions, right? So it may be 20%, it may be 30%. So that is denoted by alpha. So the number of moles dissociated and total number of moles we are basically taking or dissolving in the solution, right? So if we can also convert, so if alpha is basically in the fraction, so suppose 50% means 0.5. So if we multiply with the 100, so we will get the percentage of dissociation. So alpha is basically a fraction of number because if we take 1 mole and it's 0.5 mole is dissociated, that is the value will come with 0.5. So if we multiply with the 100, then we will get the 50%, right? So now if we can multiply the concentration terms means C. It may be molarity, it may be normality, it may be molarity. So now if we multiply the C with the alpha, so then we will get alpha C, that is the concentration of the ions of the species present in the dissociated form, right? So now here, as we are going to discuss the electrolyte, and in the electrolyte you have seen that acids and bases, strong acids, weak acids and bases comes to the strong electrolytes, strong acids, and weak acids are the weak electrolytes. So now we need to understand what is basically acid and base. So from 8th standard onwards we are basically studying acids and bases. But the concept of acid and bases are not that much simple, right? So there are lots of concepts are there. So usually a 10th standard student understand the acid means which gives H plus and base means which gives OH minus, and acid and base react together and produces salt. So like if we take an example like NaOH and HCl. So after reaction it will give a NaCl and water, right? So that is the only concept we are having so far about the acids and base, but it's not so simple, right? So there are different types of concepts exist about acids and base, so that we need to understand. So organic compounds can also act as a base, right? So like let's have some example, ammonia, pyridine. So but that this compound do not give OH minus, but still they are considered as a base. There are some acids which doesn't give H plus, right? Do not give H plus, but still they are considered as an acid. So Lewis acid in the Friedel-Crafts acylations we have studied. AlCl3 as a Lewis acid or the catalyst used in the reaction, right? So but AlCl3, if you dissociate AlCl3, it will never give you H plus, right? So there is no H plus present in the AlCl3, right? But still we consider AlCl3 as an acid. So that's why there are other concepts exist of the acid and bases. So now we need to study that what do you mean by different types of acids and bases, right? So now first concept we are going to study here, that is the Arrhenius concept. Arrhenius concept of acids and bases. So this concept we already studied in the 8th standard one, right? So we have been studying from 8th standard on. So this concept is the most simplest concept, where according to the Arrhenius, the species which give H plus are called acid. So and the species which gives OH minus are called bases. So now here, so what is acids and bases? So now let's try to understand with the example. So if we consider, let's say, example. So HA here is given as a representative example. So instead of HA we can take real example like HCl. So HCl if you give, it will give you H plus plus Cl minus. So we can also take the example like HNO3. HNO3, what is the name of HNO3? Nitric acid, right? So it will give us H plus plus NO3 minus. Similarly, we can also consider the examples of H2SO4. That will give us H plus plus HSO4 minus. So these all are strong acids, right? So let's try to understand with an example of a weak acid. Weak acids are acidic acid. So acidic acid is considered as a weak acid, right? So it will give you H plus plus CH3 COO minus. So what is the name of CH3 COO minus? What? Snail? Acetic acid, the name of this is the acetic acid. So now I am asking what is the name of this anion. So like for nitric acid it is nitrate. For hydrochloric acid it is chloride. For H2SO4 it is hydrogen sulfate. So now what is the name of this anion? Acetate anion, right? So it is called as acetate anion. So in organic chemistry nomenclature we have studied this thing. So acetate functional group, acetic acid and all. So now the bases increase the concentration of OH minus. So there are lots of bases we know. So that NaOH if we consider, so NaOH can also give Na plus plus OH minus. So now lithium hydroxide Li plus OH minus. So here. So now this is the called dissociations, right? Dissociation of the acids in the aqueous medium, and it is giving corresponding cations and anions. In case of base, cations and hydroxide anions. In case of anions and H plus. So now here I am giving you one example. Have you heard this name of the boric acid?
Yes.
Huh? Boric acid? Caramel. So boric acid, what is the formula of boric acid? So here I am giving you the formula of boric acid, H3BO3. Huh? That is the boric acid. So now how boric acid will dissociate in the solution? Can you write it? How boric acid will undergo dissociation, right?
H plus H2BO3.
Okay, this is not so simple. So this is the homework. So you search in your books or whatever resources you are having and try to get the dissociated form of boric acid. So H plus it will definitely give. So along with H plus, what anion it will give and what will be the name of this anion, right? So that is the homework, right? So now Arrhenius acids and bases are very simple. So we understood. So is there any doubt? No, right? So but slowly we need to understand a little bit higher or other concepts of acids and bases, right? What are the other concepts of acids and bases? So now next concept is Bronsted-Lowry concept of acid and base. So although the concept is very simple, but identifying acid and bases using this concept is not so easy, right? So you need to study more, then only you can identify the Bronsted-Lowry acid base. So it is very simple, like that the species that donates protons. Protons means nothing but H plus, like Arrhenius. Those Arrhenius acids are also considered as a Bronsted because Arrhenius acid gives us H plus.
Yes.
Similarly, Bronsted acid will also give proton H plus. So that means Arrhenius acids are also Bronsted acids. But concept changes in case of bases. So now, if we go to the definition of Bronsted bases, so the species that accept protons. So now, how will you explain this thing? The species accept protons. Any species which accept protons, but that means H plus ion. So now, let's say OH minus. What happens when we react OH minus and H plus?
It gives rise to H2.
H2, that means it is accepting proton, isn't it? So hydroxide anion is also a Bronsted base. This is not the only example. We need to study the other example as well. Let's say ammonia. Ammonia, what is called this two dot?
Lone pairs.
Lone pairs. So now ammonia can accept H plus and gives us ammonium cation.
NH4.
So now here ammonia is a Bronsted base, right? So because it can accept H plus. Similarly, pyridine. There is also having lone pair. It can also accept H plus and gives us the pyridinium cation. Pyridinium cation. So this is also called as a Bronsted basis. So now, if we try to understand the limitation of Arrhenius acid and bases. So why we need to go to the Bronsted acid, or why we need another concept of acid basis? Because there are some limitations present in the Arrhenius acid base. Because what are these limitations? Arrhenius acids can't explain the basicity of ammonia pyridine, but Bronsted acid base theory easily explain the basicity of ammonia and prepration. So that is the drawbacks of Arrhenius acids, which in case of Bronsted acids these drawbacks are removed, right? So is it clear what is the drawbacks of Arrhenius acids? We know ammonia is the base, but according to the Arrhenius theory we can't explain the ammonia is a base, because if you dissolve ammonia it will not produce OH minus. But according to the Bronsted concept, as it can accept H plus and gives ammonium cation, so that's why it is a base. So Bronsted acid base theory easily explains the basic nature of ammonia, whereas the Arrhenius acid base theory fails to explain the basic nature of ammonia. Right? Similar example for AlCl3, I told you previously. AlCl3 is also an acid that the Arrhenius theory can't explain. Even Bronsted theory also can't explain. Right? So for that we need to understand another theory. Right? I am coming it later. So now the next slide will go. So that is the conjugate acid base pair. Conjugate acid and base pair. So this conjugate acid base pair concept comes in the Bronsted acid base theory, right? So Bronsted acid base theory. So let's say this HA is a acid, B is the base. So now according to the Bronsted theory, HA can give H proton, so it's a Bronsted acid. B can accept proton, so it's a Bronsted base. So after reaction, what we'll get? We'll get A minus and Hb plus. Hb plus. So H plus is going from HA to B. So that's why it is a Hb plus. And then there is a removal of a proton in case of HA. So that's why we are getting A minus. Fine. So now we try to understand this thing, the conjugate acid base pair. So now initially HA is the acid. So after removing this, removing the proton, or so when HA releases the proton, so then it's converted to A minus. A minus is the conjugate base of the Bronsted acid, or B is the initially Bronsted base. So now after accepting the proton, it converted to Hb plus. So Hb plus will be considered as a conjugate acid of Bronsted base B. A minus will be considered as a conjugate base of the acid. Hb plus will be considered as a conjugate base of the conjugate acid of the Bronsted-Lowry base. Right? So this is called a conjugate acid base theory. So this theory actually helps us to understand or to compare that which acid is a stronger acid and which acid is a weaker acid. So let's try to understand with a very simple example. So if the conjugate acid is more stable, then the basicity is higher. So if we compare, so let's try to understand with an example. So suppose if we compare two species, let's say HA and HB. Now when HA dissociate, it will give H plus and A minus, and when HB dissociate, it will give us H plus and B minus. Now HA is the acid, HB is also acid, A minus is the conjugate base of HA and B minus is the conjugate base of HB. So now if we want to compare the acidity of HA and HB, so how we will compare? We need to check the stability of A minus and B minus. So if A minus stability is higher compared to the B minus, that means HA is stronger acid than HB. Right? If A minus stability is higher compared to the B minus, then we will call HA is a stronger acid than Hg. Similarly, we can also explain in terms of other. So let's say X and Y, both are bases. So they will accept H plus Bronsted bases, and it will form XH plus, and Y also accept H plus, and it will form YH plus. So now these are two Bronsted bases. These are the conjugate acid of X and Y. XH plus is the conjugate acid of X. YH plus is the conjugate acid of Y. So now if somebody asks you compare the basicity of these two X and Y, or which one is more basic, so then we have to compare their stability of conjugate acid. If XH plus is stability is higher than YH plus, then we call X is a stronger base than Y. If YH plus stability is higher than XH plus, then we call Y is the basicity of the Y is higher than X. So this conjugate base or conjugate acids stability helps us to identify the or to compare the acidity and basicity between different types of acids and bases, right? So there is another concept is there. So that is I haven't included in this slide because it is not there in your syllabus. But if you want to prepare for competitive exam, so that you need to learn. So that's why there is a concept of Lewis acid base theory. So now there are some limitations. That's why we need to go for another theory. So Bronsted, what is the limitation in case of Bronsted acid base? Although Bronsted acid base can successfully explain the basic nature of ammonia pyridine, but it fails to explain the acidic nature of AlCl3, BCl3, those compounds. AlCl3, BCl3, they are acids, but this neither Bronsted theory, Lowry theory, neither Arrhenius theory explain the acidic nature of AlCl3, right, or BCl3. So for that we need to study another acid base theory, that is called Lewis acid base theory. Lewis acid base theory, right? So now just again revising things. Arrhenius acid base theory, acids are those which gives H plus, bases are those which gives OH minus. Bronsted acids are those which gives protons H plus, and bases are those which accept H. Now here this Lewis acid base theories is based on the concept of lone pair. Have you heard this word, lone pair? The free electron present in the molecule, right? So now according to this theory, lone pair acceptor. So if any species which accept lone pairs, these are called acids. And lone pair donor, right? These are considered as a basis. So this is a complete different concept, right? So this concept is based on the lone pair, right? So if the species or any species which accept lone pairs, so then we will call it a Lewis acids. If it donates lone pair, then we will call it a Lewis basis, right? So let's try to understand with examples. So now, what are the examples of Lewis acids? So AlCl3, BCl3, and what are the examples of Lewis bases? Ammonia, pyridine. So ammonia, pyridine, both it can be considered as a Bronsted basis. It can also be considered as a Lewis basis, right? But Arrhenius, it is not a Arrhenius basis, right? It can't give OH minus. You can tell that ammonia is a Lewis base. It can also tell ammonia is a Bronsted base, right? AlCl3, BaCl3 are the acid only in the concept of Lewis acid base theory. Arrhenius acid base theory can't explain the acidity or the or even Bronsted acid base theory can't explain the acidity of this AlCl3 and BaCl3. So now you can easily understand it's having lone pair. So now it can easily donate this lone pair to the any electron deficient species, right? But how this AlCl3 BCl3 behaves as acids, right? So that we need to understand, right? So now to understand this, we need to understand little bit the structure of this AlCl3 and BCl3. So BCl3 structure is very simple. So if you remember the boron, what is the atomic number of boron? 5. So now atomic number is 5. So you can write electronic configurations, right? 1s2, 2s2, 2p1. So now we know that outer shell electrons or outer orbital electron participate in the bond formations or molecule, it participates in the hybridizations. So now if we write, so boron, that is the 2s2 and 2p1, that is in the ground state. So now if we bring it in the excited state, so now we can write like this. Like this. So now 3Cl, BCl3, what is the structure of BCl3? 3 chlorine are there. So each chlorine will give one electron. So now Cl, 1Cl, 1Cl. So now if we carefully see the structure of BCl3, BCl3 is not fulfilling its octet. So this is a, how many electrons are there? 6 electrons. So it's a, and one vacant orbital is there. Vacant orbital, right? So this vacant orbital, to fulfill its octet, it can accept lone pair for any electron donating species, ammonia or any other species which can donate the electron. So that is the reason why BCl3 act as a Lewis acid. And boron, aluminium, they are present in the same group. So the aluminium also having vacant d orbital. So that's why aluminium AlCl3 can also accept the lone pair. So according to the Lewis acid theory, any species which can accept electron are considered as a Lewis acid, right? So even in the cations means any cations, metal cations, lithium plus, sodium plus, magnesium plus, this can also accept electron because these are the electron deficient. So these are also considered as a Lewis acid, right? So now if we try to write the reactions between Lewis acid and Lewis base, let's say BCl3 and ammonia. So what will be the product? The product is little bit interesting. They forms adducts. And why we are drawing this type of bonds? So NH3 will be plus and BCl3 will be minus. So this is called coordinate covalent bond. So where the nitrogen is giving the lone pair 2 electrons, but these 2 electrons are getting shared between nitrogen and boron. So that's why it's called coordinate covalent. So is it clear? It is clear what is the Lewis acid base concept? So it is important for a competitive examination. So if you want to prepare for JEE or CET or any NEET, so then this type of questions you may expect, right? But in your syllabus it is not there. Slowly we can proceed. So the next important thing is the Oswald Dilutions law. So Oswald Dilutions law. So why this word dilution is there?
dilute with acid or base.
So this law basically tells us how the degree of dissociation is related to the concentration. So concentration, you know, all of you. So molarity, normality, molality, these are concentration. What I told you, the strong electrolyte and weak electrolyte. Strong electrolyte dissociate 100%, right? So there is a no dilution effect for strong electrolyte. So if we take high concentrated solution, it will 100% dissociate. If we even take the low concentrated solution, it also 100% dissociate. But things become interesting when we consider the weak electrolyte. So weak electrolyte, what are the weak electrolytes? Weak acids and weak bases. So now what happens if we dilute the weak acid weak base solution? So whether the degree of dissociation will change or degree of dissociation remain same. So that what is the relations between degree of dissociation and the concentration for weak electrolyte? To understand this, we need to study Oswald dilution. Again, I am repeating: strong acid, strong base, strong electrolytes, any salts, concentration, whether you take high concentrated solution, low concentration solution, degree of dissociation remains same. 100% dissociation takes place. There is no relations with the concentration and degree of dissociation for strong electrolyte. But things become interesting when we consider for weak electrolyte. How the concentration affect the degree of dissociation in case of weak electrolyte. So that we basically need to study in case of Oswald dilution. So you can see the application of this mass action law, weak electrolyte, and is known as Oswald dilution law. So from this, whenever we will talk about Oswald dilution law, so it should be clear to you that we are going to talk about weak electrolyte, not strong electrolyte. So now there is a equilibrium, dynamic equilibrium existed between undissociated molecules of the electrolytes in the solution, and the law of mass actions can be applied and consider a law of mass actions. Can you recall what is the law of mass actions? Chemical equilibrium we have studied. What is the law of mass action? Sneha? I think you are telling out the laws of thermodynamics. Energy neither be created nor be destroyed. So dissociation is a type of reactions, right? So suppose if you take NaCl, it undergoes dissociation, Na plus and HCl minus. So now so that's why I always tell you, so you need to revise the things, right? So NaCl, right? So if you write NaCl dissociation, equilibrium Na plus Cl minus. So now we can write equilibrium constant. So equilibrium constant, the concentration of product by concentration of reactant. So this, how we can write this? This is coming from the laws of mass actions. So rate of forward reactions is the product of the concentration, right?
Yes.
So what we can write? Rate of forward reactions is the okay, forget about the forward rate of law of mass actions. So now here we basically going to use the concept of chemical equilibrium. This chemical equilibrium actually comes from the laws of mass actions, right? So now so suppose we consider here AB is a weak electrolyte, right? So now AB undergo dissociation A plus and B minus, right? So let's say before undergoing dissociation, let's assume the concentration is C. So now it is undissociated form, so there is no A plus and no B minus. So initially the concentration of A plus and B minus will be 0. So now, so here as AB is the weak electrolyte, so we need to bring the term the degree of dissociation. So degree of dissociation is applicable only for the weak electrolyte. So degree of dissociation, what we can write at equilibrium, C into 1 minus alpha is equal to C alpha. For C alpha concentration will get for A plus, and C alpha concentration will get for amount, or C alpha amount will get for B minus. So now equilibrium constant, what do we mean by equilibrium constant? K is equal to concentration of A plus into concentration of B minus divided by concentration of AB. So instead of A plus we can write C alpha, instead of B minus we can write C alpha. So now, and instead of AB, what we can write? C into 1 minus alpha. So why we are taking 1 minus alpha? That is very important to understand. So let us assume initially it is 1. Degree of dissociation, I always told you, it comes in the fractions. It's a 1 means the highest number. So 1 is the initial AB and let's say 50% undergoing dissociation. So 1 minus 0.5, that is the degree of dissociation. Alpha is 0.5. So let's say 50% of AB undergoing dissociation, or 50, alpha is 0.5. So 1 minus 0.5, 0.5 into C, 0.5 into C. So similarly we can write C alpha, C into 1 minus alpha, C alpha square by 1 minus alpha. So now here one mathematical assumption we need to take. So K is considered is an ionization constant, like an equilibrium constant, nothing else, nothing different. K is also considered as an ionization constant. For weak electrolyte, if we consider alpha is very small, so its alpha is almost negligible compared to 1, right? So 1 minus alpha is equal to, we can write 1, right? If alpha is very much negligible or is very less compared to 1, so what we can assume here, alpha is less than 1, right? So then what we can write, 1 minus alpha is equal to 1, right? So now here we are putting this assumption, 1 minus alpha is equal to 1. So what we can write, K is equal to, so what we can write, K is equal to C alpha square, C square alpha square by C. So C will cancel out, C alpha square, K is equal to C alpha square we are getting.
Yes.
So K is equal to C alpha square we are getting here. So now alpha is equal to square root of K by C.
Yes.
So now if we, K is the, what we call, K is the ionization constant, equilibrium constant is the constant term. So what we can write, alpha is proportional to 1 by square root of C. So that means that degree of dissociation is inversely proportional to the square concentration terms of square root, inversely proportional to the square root of concentration. So that means if we increase the concentration, alpha will decrease. If we decrease the concentration, alpha will increase, right? So if we dilute the solution, more and more number of ions will be generated. If we increase the concentration, less number of ions will be generated. So this is the relation actually we get from the Oswald Dilutions law. So this is only applicable for the weak electrolyte, and what it tells that degree of dissociation is inversely proportional to the square root of concentration. So now if we increase the concentration, degree of dissociation will be less. If we decrease the concentration, degree of dissociation will be higher. But this law doesn't applicable for strong electrolytes. Strong electrolyte always dissociates 100%, right? So is it clear?
Yes, sir.
So now So properties of water. Water is a very important solvent, right? So water is a very important solvent, and acid base basically we so whenever we talk about acid base, mostly we consider water as a solvent. And water itself ionizes. So how water ionizes? Water so now how water ionizes? Water ionizes. So if we consider water, this is called the auto-ionizations of water, right? So if you take two water molecule, it gives you H3O plus OH minus. So now, so water acts as an acid as well as base according to the Bronsted acid base or the Lewis concept. It can only take the lone pair, so that's why it is a base. So now why it's a water? So if you simply dissociate water, so it can give H plus and OH minus. So that means water can give H plus, so it is a proton donor, so it can be considered as acid. It gives a OH minus, so that is also considered as a base. So a very interesting molecule, right? Water, it can also be considered as acid, it can consider as a base as well, right? So now how much H plus it gives and how much OH minus will give, and what is the ionic product of water, that we need to know. So that will help us to understand the pH scale. So what do you mean by pH scale? So it's a scale that will help us to identify that whether a solution is acidic or a basic. So pH scale. So this pH scale comes from the water only. So this pH scale is applicable in the water solvent only, right? So that's why we need to understand the dissociation of or ionic product of the water, right? So now if we write, so let's say this is an equilibrium process. So now we can write Kw is equal to H plus OH minus upon H2O, right? H plus OH minus upon H2O, right? So now this is called ionization constant of water, Kw. So what is the value of Kw? The value of Kw is 10 to the power minus 14. So now, so that means in water is, we consider that the activity is 1. So that means H plus into OH minus is equal to H plus into OH minus is equal to 10 to the power minus 14, or we can consider that 10 to the power minus 7 into 10 to the power minus 7. That means if we dissociate water, it will give 10 to the power minus 7 concentration of H plus and 10 to the power minus 7 concentration of OH minus, right? So the ionic product of water is 10 to the power minus 14. So that you need to remember, and that is at 25 degrees centigrade experimental conditions, right? So now we need to understand what is the pH. So pH is a basically scale. So it basically scale from 0 to 14. So now students sometimes get confused. So that why this scale is 0 to 14, not 0 to 20 or not 0 to 10. This 14 value is coming from this dissociation constant of water, right? So now the 7 is the middle point. So any species which gives the pH less than 7, that is the acidic. Any solution which gives the pH more than 7, that will give you a basic, and 7 is the neutral. So pH is 7, that means neutral. pH less than 7 acidic, pH less than greater than 7 is basic. So now what is pH? pH means power of hydrogen. pH, there is a relation, pH is equal to minus log of H plus. So, and then what is the POH? POH is nothing but minus log of OH minus. So if we know the concentration of H plus and OH minus, we can easily calculate the pH values of the solution. So now the next slide we are going to understand or going to learn how the pH and pOH are.
How the value of Kw is derived 10 to the power minus 4.
So Kw is an experimental value, so it's not derived value. So after performing experiment, then only we can get to know the value of water is, dissociation constant of water is 10 to the power minus 4. It's not a derived value, so it's an experimental value. So now that's why this pH scale is basically 0 to 14. So if we would have got this 20, then the scale will be in between 0 to 20, right? So now pH means power of hydrogen, pOH means power of hydroxide. So what is the relation? pH is equal to minus log of H plus concentration, and OH is equal to minus log of OH minus concentration, right? So now in next slide we are going to discuss how the pH and pOH are related, right? So now this is a very simple. So now what we can write? So here I have so now we know water means it dissociate H plus and OH minus. So now what we can write? Kw is equal to H plus concentration of OH minus. So same thing we have written H3O plus, or H plus instead of you can also write H3O plus. If you take two water molecules, so that you can write H3O plus OH minus. So that's nothing. H3O plus is nothing but H plus water. That is called H3O plus. Hydronium anide, right? So now Kw is 10 to the power 14 we know, and H plus and OH minus is the 10 to the power minus 14 is equal to the multiplication concentration of H plus into concentration of OH minus. So now if you take both side log, right? So I hope you have studied the log in the mathematics. So if you take both side log, so what we can write? Log of A into B means log of A plus log of B, right? So what they are taking? They are basically taking minus log, and log of x to the power y means y will coming forward, and then log 10 means 1. Log 10 means 1. Here they are putting log 10 is 1 and 14 is coming forward, and minus 14 into minus, that means we are getting plus 14, right? And log of A into B means log A plus log B. So here as we have taken minus log, so the minus term will be there. And in the previous slide we discussed that pH is equal to minus log of H plus, and pOH is equal to minus log of OH minus. So now instead of minus log of H3O plus, we can write pH, and minus log of OH minus we can write pOH. So pH plus pOH is equal to 14. So that is a very important relation. So we need to remember that pH plus pOH is equal to 14. So now from these equations, what we can, if we know the pH, we can calculate the pOH. If we know the pOH, we can easily calculate the pH. So now these are the two numericals. Try to solve. So now what is the pH of 0.05 molar solution of hydrochloric acid? And what is the pH of 0.02 molar of sodium hydroxide solution? So interestingly, both the cases in the I have given you the strong electrolyte, right? HCl and NOH both are strong electrolytes, strong acid and strong base, right? So we need not to consider the degree of dissociation. Alpha we need not to consider here. 100% dissociation will occur.
Yes.
So that means, so if we try to understand the question number 1 solution, so that so now for answer of question number 1, so what is the pH for 0.5 molar solution of hydrochloric acid? So what we know, pH is equal to minus log of H plus. So now HCl, how it dissociate? HCl 100% dissociate. So now 0.05 molar HCl will gives you 0.05 molar of H plus and 0.05 molar of Cl minus in solution, right? So now very simple, here we have to put log of 0.05. So now you can easily get the value of pH. So how much you will get? Just calculate it. You do the calculation and let me know what is the value.
Final answer, sir.
Final answer.
9.
9?
pH.
How come it becomes 9? Because pH is the acid.
I thought the final answer. The pH will be 5. pH will be 5. 5 will become minus 2.
How come it will become 5?
So there is given 5.
There is given 5.
2 point shift.
So do you know what is log table? How to calculate log value? Log of 5 by 100 we can write. So log of x by y means log x minus log y. Log 5 minus log of 100. 100 means 10 square. Right? So that means minus of log of 5 plus 2. So what is the value of log 5? That you have to either you have to use log table or you have to use calculators to get the log 5. So how come so we are getting 5?
Zero point
0.69.
Yes, sir.
So that will be but 2 minus 0.69. So that means 1.3 or some 1.31 something it will come. So that means it is acidic less than 7. So this is how we have to do the calculation. Is it clear?
Yes.
So next try the second one. Shall I remove it?
Yes.
So now question number 2. What is the pH of 0.02 molar of sodium hydroxide solution? Right? Here we have to calculate the pH. But what we know, sodium hydroxide dissociate and gives us sodium plus OH minus. So now here we have as sodium hydroxide strong base, so it is a strong electrolyte, 100% dissociation, no need to consider the degree of dissociation. So here we will take 0.02. If we take 0.02 a molar of sodium hydroxide, that will give you 0.02 molar of sodium plus and 0.02 molar of OH minus. So now here we need to use POH formula. So POH is equal to minus of log of
OH minus, right? So now same, here we will put minus of log of 0.02. So and like previously here also we will get the
2/100.
so similar calculation. So minus log 2 minus log 100 means 2 log 10. So 2 log 10 means 2. Here what is the value of log 2?
0.30.
30
Yes.
minus 2.
1.70.
So plus 1.70 you get.
Yes.
Huh? So that is the value of POH. But in the questions they have asked to calculate the value of pH. So now here we need to use this equation, pH plus POH is equal to 14. So once we need the POH 1.7, so the pH value will be
12.3.
so pH value will be
12.3.
12.3. So that means it is above 7. So that means it is basic solution. Previous one acidic. This is acid we have taken. This is the basic sodium hydroxide. So one simple trick here I am telling you. So those who are preparing for CET or JEE mains. So for that here I am giving questions you try to solve at your home. So now suppose if we what will be the pH of 10 to the power minus 6 molar HCl solution? What will be the pH of 10 to the power minus 6 molar HCl solution? That is very simple. So we will take pH is equal to minus log H plus. So that is 10 to the power minus 6. We will get 6. So pH is equal to 6. So HCl is given, pH is equal to 6, right? So now if we keep on diluting this acid, so we can prepare 10 to the power minus 8 molar HCl solution. It is also possible. 10 to the power minus 2, 10 to the power minus 4, 10 to the power minus 6, 10 to the power, if we keep on diluting, adding water. So acid concentration will decrease. And then this is the 10 to the power minus 8 molar. So now if we calculate the pH, so what will happen? Log of 10 to the power minus 8. That means 8. So the acid become base. Is it possible? We are giving acid in the water and its pH is giving 8. So this acid is converted to the base in the presence of water. Is it possible? So just try to find out the answer of this. So what will be the pH of 10 to the power minus 8 molar HCl solution? So that is the homework. What will be the pH of 10 to the power minus 8 molar solution? I think it's done. So next class we will discuss the other things. We will continue the solution. I hope we could finish this ionic equilibrium in the next class. Right? So, we can stop.